It's my pleasure to introduce Elchanan, who will tell us about affine Grassmannian, affine flag variety, and their homology.
Thank you.
Let me go somewhere.
Yeah, thank you. Yeah. So yeah, as Daniel said, they're going to be affine Grassmannian. They're going to be cohomology. I don't know how much I'm going to talk about affine flag variety, but we'll see. So please affine Grassmannian, which is with two S and two N's. Very important. Equivariant cohomology. So I will start with a reminder on what we did in the past weeks. So we were computing, looking at a special, like some like the equivariant cohomology ring. So G equivariant homology of G mod B times G mod B. With convolution structure. So the goal for today is basically to find an affine analog. So to begin with is to define what is affine analog, but then I guess roughly speaking, when we say affine analog, we mean instead of moving from X to the loop space of X, so pointed loops. Of course, we will need some algebra or geometric version of that. But one of the problems is that then even if X is a variety, like something finite dimensional, this will usually not be finite dimensional. But the idea is just doing everything but adding loop everywhere. Okay, so I will start by defining the geometric objects that we're gonna work with. So first of all, definition, I'm gonna define the loop of G. So G is, maybe I will write it. G always gonna be, I mean, I don't know, it's not really. As always, G is a reductive group and everything is over C. So this definition of loop of G will work for any scheme, not just group, but for us, it's just going to be a group. So it's going to be like, let's say, home from spec to loop of G is going to be defined as G R bracket G point of G. So the value, so this is basically like the space of, or maybe let me write it again. So this is the space same as from D star to G. So D or star, this is the punctured formal disk parameterized by R. So this is basically the spectrum of that. Not really, but close enough. And we want maps from the punctured disk to G. So this is basically the analog of loop space. Punctured disk looks like a loop. Some commutative algebra over K over C. So yeah, I mean, you can just take that as a definition, maybe like up to technicalities. This is space which just home space from D star from the function disk to G, and then inside of that there are going to be positive loops. So this is basically like in topology that will be like loops that can be extended to the whole disk, so like trivial loops. So this is going to be G of square bracket T. So also from D to G. So let's say, okay, so first of all, what type of objects those are? So as I said before, a loop will usually be something infinite dimensional. So this is going to be also the situation here. So let me start with positive loops. So I can write that. So the space of positive loops can be written as limit over the following spaces. So R goes to G T mod T to the N. So we can write it as a limit over space where we take like our points are going to be some like nth neighborhood of just a usual G point. So each one of those is a scheme. So this is going to be some scheme of infinite type. So it's still a scheme, but it's a limit over things that might be of finite type. So this is going to be of infinite type. Loop of G is even, so this one is already a problem. It's of infinite type, but this one is even worse. This one is going to be an int scheme of infinite type. Not going to be very important for what I'm going to talk next. I'm just going to want to explain why there are like, there are going to be problems with working with those objects. Goes to G E minus M T N R T. So now I can take bigger and bigger ends and smaller and but allow bigger and bigger poles, and then I take colimit and limit. So the object I'm getting eventually is an int scheme of infinite type.
Sorry,
Where is
T minus M R T?
Yeah, you just take
It's not
oh yes. That's right. Yeah, I guess you should take colimit over the multiplication by T map from L plus G to itself. I believe this is supposed to work. Anyway, we are not going to work with loop of G. Like loop of G is going to show up, but not in like we won't need the schemes or in scheme structure. Okay, so an example for how it looks like. So if I'm taking G to be G of A, then positive loops of GA, this is going to be spec of the A1, A2, so we're going to have polynomial ring with infinitely many variables. So each variable corresponds to if we think about a point like an LG, our point of LG as a choice of let's go here of a polynomial of a Lorentz series of a Taylor series, let's say here, then those correspond to the coefficients. So each coefficient gives an additional dimension, and then loop of GA is going to be polynomial spec over I, and this goes to minus infinity. So now instead of starting with 1, I'm starting with lower and lower numbers, and then I'm taking colimit. So you can still write it with dots, but then it will be very confusing because the three dots here and here will mean two different things. So this is going to be basically union of spec of infinitely many variables, but when you start the variables lower. Okay. So now finally definition of the affine Grassmannian, which is the object we are going to work with. So I'm going to define it by its functor of point, just because that's how it shows up in most references, even though for us, it's not going to matter that much. So first of all, I'm going to define the affine Grassmannian as the scheme that assigns to a commutative ring R the following space of pairs E and alpha. So E is, let's say this number G. G bundle over the following disk, with the R following disk, so a spec of R of square bracket T, and alpha is the trivialization of the restriction to the puncture disk. So E0 is the trivial one. So every G bundle over the disk is trivial, but you can change the trivialization by basically choosing for each point of the disk an object. It's like a function, any section from B to the trivial bundle can give you an automorphism of the bundle. So we are choosing a G bundle over D, which is abstractly trivial, but then we're choosing a trivialization only on the function. And then, I guess the main point why I introduced all of this stuff there. So I can define a map. I have a map from loop of G to the Affine Grassmannian. And this map is going to be, if I have an element here. So remember, this is an element here. It's like a map from the formal disk to G. For the formal puncture disk to G, sorry. So this will go to the trivial, just take the trivial bundle and take this object as your trivialization. So if I have a trivial bundle, choose a trivialization of that over the puncture disk is to just choose a map from the puncture disk to G. Right, like automorphisms of a G bundle, of the trivial G bundles, with like functions, like functions from the space to G. Let's see right now. Morphism of trivial bundle, I mean in general. X over X as a G bundle are the same as map. So here X is the formal disk, the formal puncture disk, so it's mapped from the puncture disk to G. So it's an object of LG. So this gives us a map from LG to the affine Grassmannian. It's certainly, I would say, subjective. It's like every object here can be written in that way. Like we only have one bundle, it's the trivial bundle, and then to choose a trivialization of the trivial bundle, as I said here, this is exactly choose an element of LG. So the question is, what are the fibers?
Sorry, how do we define G bundle? It's like a map. Yeah, so what is it?
So what is the definition of a G bundle here? I mean, you can see like a map to what
spaces reflection G. Yes.
Yeah, like you can always, yeah, you want something that locally look like that. Everything will locally look like that. So
yeah,
a scheme that is abstractly isomorphic to D to the disk time G is
if you define G bundle over disk as like trivial bundle, then of course, but maybe some kind of statement, then I just forgot what kind of statement.
I believe you define BG, like you define the scheme, like they stack BG and then you take maps.
Okay, well, yeah.
It's a definition. I don't know. I don't think there is like a way to. Maybe there is. I'm not aware of a way to define it like as a locally trivial. If you work over this, it's kind of meaningless. Yeah. I mean, yeah, you can say it's a locally trivial G bundle, and then you realize that locally over a disk there is only one option, everything, and then it's a trivial. Anyway, all of that is not very like the let me finish the statement and then lemma. This is a principal L plus G bundle. So that just means that the fibers are exactly L plus like positive loops, and proof is kind of straightforward. So fiber of a given E0 and gamma is going to be, so we can, in the fiber, there are going to be other choices of trivializations, but they're supposed to be, but if I'm changing the trivialization, I have to change the bundle so that I will end up with the same thing. So collection is 0, and then betas for beta positively. So we are taking up to isomorphism of the bundle. So isomorphism of the bundle over the entire disk is is given by an element of positive loops. So if I have a bundle here, I can change it by an element of positive loops, and then I have to change that too. And I am getting an element that will map to the same thing in the Affine Grassmannian. So yeah.
Sorry, what's a positive loop?
Positive loops is a map from the non-puncture disk. Yeah, so like it is like topologically, it means like a loop that is trivial. You can extend to the disk itself. But here, this is just literally the definition. So you don't have poles. You have like some. I mean, let's say like an element of, let's say, like yeah. I mean, let me write down like LG L2. So of L2, this is going to be like matrices of the form. You have F. Sorry, F11, F12. That the determinant is not 0, and Fij are like Laurent series, so they have pole, and then positive loops are when they don't have pole. Okay. All right. So, got it. I mean, okay. So, corollary of the lemma is that the affine Grassmannian can be described as the quotient of LG mod L, which is sometimes the definition that is given for what is the affine Grassmannian. It's the quotient of loops by positive loops. What do I mean by quotient? So you need to take shiftification, but I will F P Q C shiftification of the quotient.
Yeah, trying to like people never write that over C. Like, is it are they just wrong, or like do we only like when do we need this shiftification? Is it?
Wait, why do I need the shiftification here?
Yeah.
I mean, this is not about C. This is just like the locally if you want to be something to describe something that is locally trivial, like even forget about it, just BG needs a shiftification because just BG will only give you like just if you just construct like the set theoretical quotient, or I don't know how to call that, then you will just get trivial bundles. You will get a single like a map to a point mod G will give you a single object and automorphism G. This is the trivial bundle. If you want to get something that is maybe locally trivial but not globally trivial, this is exactly shiftification. So you want to say locally it is what we started with, but then you change. So same thing here.
Yeah, but it seems that you just described like scheme quotient. You took three factors of points, and then applying one factor of points is LG of R over L plus G of R. Where do we?
This, I mean, if you take quotient at the level of factor of points, then you will get something which is not a shift.
We
Yeah.
can not only spec varieties. Okay, yeah.
This is the
When you say G subscript R, what's the subscript R mean? Like with this?
Spec of that. It's just like I have the function like the formal disk is defined as K, like the C with like power series in C, so power series in R. Okay, which is like almost the same as R tensor power series with C, but you have to take completion. So maybe okay, so this is the division of that, and then let's just put like one example. Okay. So the Affine Grassmannian of let's do GLN and then I will do GL1. So Affine Grassmannian of GL1. So as I said here, by the definition was a G bundle and a trivialization over the puncture disk. So a G bundle, in the case of GLN, a GLN bundle is a vector bundle, which is like so a local like a projective and finitely generated model. So this is going to be the same as spaces projective and finitely generated. Let's say C, P, and modules, and then we want
CT modulo from N.
if of Franken. So yes, rank. And then we want a trivialization after we restrict. So we want a trivialization after we restrict to the puncture disk, which is moving to Lorentzius. So that's module, let's give it a name. So lambda, so and we want an embedding of that into the trivial bundle after we invert, after we restrict to the puncture disk. So this is basically the definition of a lattice. The and lattice. And which is another common definition of the affine Grassmannian. And then in the case of Grassmannian of GL1, okay, so this is just C star. So then, I mean, so a CT lattice, so it's going to be like some, you're going to be determined by basically where you start. Like if you started in T to the N. So this is like the collection T to the N, T or N and Z. So this is basically And then somehow we could just replace projective by free, right? Because it's some local ring that we
Let me
work over, right?
louder.
That was the opposite of louder.
Opposite of louder. Yeah, sorry. Say it again so that everybody hears.
Yeah. And just in the definition, right? We can just replace projective by free, right? Because it's some local ring that we.
Yes.
Yes, huh? Okay, thanks.
Yeah. Everything here is trivial. Yeah, I just want to repeat the definition of the vector bundle, but yes.
Just for serious projects, it's unique factorization domain or something.
Okay, and then I guess, a statement that I'm not going to prove, but can be kind of seen by what we've already seen. So claim G is in finite improper and in scheme. Should insert in everywhere. So what that means, we can write it as a colimit of proper schemes of finite type, and the transition maps are closed embeddings. So the main point to take from that, what the important part of that is that then we can define cohomology, like we have a well-defined theory of cohomology, equivariant cohomology, and so on. So,
and for C points, or limit is like union.
Yeah. All right, and then so I'm just going to define the next object just because it might show up, but not going to use it much. Is so Affine Grassmannian. What we did in Affine Grassmannian, I guess, I should have said it before, but I said we're taking affine version of everything. Maybe I will write it here. So, in the finite case, we used the representation theory of reductive groups, of semi-simple groups. It was very important. And here we are moving to the loop group. So why is there even a chance here? And the reason is because the loop group, or a variant of the loop group, basically will behave very similar to like a reductive group, like a semi-simple. So the Lie algebra of the loop of G. So this is loop of G. Can read it like that. Now it's linear, so it's literally just an element of this vector space, but with power series and with bracket given by just an obvious extension of the original bracket to on G to the power series, to the Laurent series thing, which is you take bracket of the Lie algebra things and you take product of the polynomial thing. And it has central extension which is denoted by G hat, which is as a vector space, just adding another copy of C. And this is the affine Kac-Moody algebra. And it has a representation theory very similar to the finite case. Basically, it belongs to an even larger class of Lie algebras, just Kac-Moody algebras, which are defined by some variant of Cartan, like a generalized Cartan matrix. So you can construct them abstractly, similar to how we construct like finitely algebras from Cartan matrix. And we get a representation theory that basically is like a very similar theory of highest weight representation and so on. Now the Affine Grassmannian here is, so what is happening is kind of, we are adding a new like simple core root. Not exactly that, but close enough, which is like a new direction, which is T. So we have all the old directions which are coming from G, and then we add T. And then the Affine Grassmannian is taking quotient by is like kind of like a maximal maximal parabolic group. Now the
Sorry, what's the gist of a maximum parabolic?
I'm just saying the Affine Grassmannian is some analog of maximal parabolic because you divide by almost everything. You just leave just one direction. Everything is just analogy, but close enough. Anyway, all of that, just because I wanted to say, like, we also have like the analog of just the like X, like G mod B, like the flag variety, which is so we define, first of all, we define the Iohari subgroup. So this is the pre-image of evaluation by 0 B subset of positive loops. So we have a map from positive loops to just G. Just this is a power series, just evaluated at 0. And then take the pre-image of B. Borel. B. This is the Borel subgroup, sorry.
Can you write an example 2 by 2 SL2?
Sorry?
Write maybe 2 by 2 SL2 example.
Yes. So yeah, let's do an example for two. So let's say G equals S2. So the condition here is we want things. So we have, so first of all, I need an element of just all loops, right? Is gonna be something like that, right? We have F, E, G, E. F11, E. So some power series with the condition about the determinant. And now we want that when we evaluate at 0, we want it to be in B. So we want it to be in B, so we want that to be 0. So it's everything just when we have T here. So when you evaluate at 0, you get this. Okay, and then definition of the affine flag variety. Sometimes it's written with AFL, sometimes not. Is the quotient of loops by, so we divide by less. Before the Affine Grassmannian, we divided by positive loops. Now we only divide by I. So they're going to be a projection map. And the projection map with fibers given by G mod B. Also has like a description in terms of maybe I will write it in terms of vector bands and trivializations. G is the same as so first of all, we have element. We have an element here. So a vector bundle on the formal disk and a trivialization on the puncture disk. But then we also want, so when the condition here is that at 0 we will be at B. So at 0 means restricted to the fiber at 0, and we want there our object to belong to B. So it's a B reduction. So this is just an element of the Affine Grassmannian. and sigma is a section of the fiber at 0. So like you choose an object of G of, if I have a bundle, I can always like a G bundle, I can always take a quotient by B and I get like G mod B bundle and I take the fiber at 0 and you choose an object there. So choosing an object in the quotient bundle is the same as taking a reduction. Like if I have a G bundle, choosing an object of G mod B is the same as taking a B reduction. This is just kind of a definition. Oh. So this is the flag variety, and then the projection is the obvious projection where we forget the B reduction. So the restriction is T. So for example, if G is GLN, that means that we take a complete, like we have a vector bundle, and then where object depends on T, and then when we set T to 0, you also need to give a complete flag. Okay.
Like sequence of like a flag of lattices. Or
Yeah, like if it's GLN, then it's I would let it right now. GLN. So sample GLN. So you need to give, so first of all, you need to give a lattice. So G is so you give a lattice and then you give also sequence. So you give a sequence of things that lie like in between your lattice and T times. So this is the same as to give a complete flag when you divide by T.
Lambda 0 is lambda.
Yes.
sorry, and here this respect is this like function of points or
So this is function of points.
no, like before like up in the
Here I just defined it by a quotient, and then I just said in terms of the
quotient, then what is
again she's like FB
Oh, okay.
quotient. Yes.
Yeah, that's
Okay. And then I will just give. So I said that this Affine Grassmannian is like topology, a geometric analog of the loop. Let me give a precise statement that I will not prove or use. So let Q G a maximal compact subgroup. And loop of K, so this is polynomial maps. From the point of S1 to point at K. Then we have a map from
What do you mean GVMs? What do you mean maximum compact?
maximal compact subgroup of G.
It wasn't G like.
Yeah, this can be like GLN.
Oh, it's like a real, like
Yeah.
sound.
No. Now we are like I mean now it's like ring, like yeah, K will have a ring. Because you've got also the proof of that is using analysis. It's not anyway. then we have a map from loop of K to the algebraic geometric version of loop of G, which is given by, so an element here, I can write it as a polynomial in EI theta, and you can send it to just T. Right? If I have a map from S1, I can an object of S1 will correspond to some object in the puncture disk. And a theorem of Siegel and another author of book loop group that I forgot the name. This is an equivalence. And so so I can take now the quotient by like compose it with the quotient, and this is a homomorphism. And
C points on the right.
and maybe I'll give just small intuition for why we expect that to be true. So let's say I have like I will write, so our definition of the affine Grassmannian was a G bundle on a disk and a trivialization on a puncture disk. So this is topologically the same as a map. So a map from the disk, so D2 to G, but we want it to send the boundary of the disk to a point, to VG, sorry. VG, so in topology, right, a bundle is this, a G bundle is described by a map to VG, and we want it to S1 and so we wanted to send the boundary to a point. So this is the same as so a map from D2 that sends the boundary of D2 to a point is the same as the map from S2, like a pointed map from S2 to BG, which is the same as loop 2 of BG, which is the same as loop G. So this is heuristic, not actual proof, but
Actually, I inspired like
yeah.
interesting this like so polynomial maps is there like polynomial on C?
So polynomial maps that you have to embed S1 inside some SO n of R, and then you write things in terms of yeah. It's like the problem is that there are many versions of loop spaces with various convergence restrictions and
this like so it's something about S1 and then like polynomial of that.
yeah.
Then you take that
And then just
polynomial.
yeah. Just instead of using that as my formal parameter, like what's my parameter is
Like if it's a polynomial does not go to L or that's my question.
No, use negative power.
It goes to
No, negative powers exist. You can flip your circle.
maybe I don't understand.
The conometric polynomials can be positive and negative, like z minus 1, z squared, z minus 2, z.
Oh, that's what it means. Okay. Sorry. Yeah.
like the point is just you don't take power series, like you don't take limits. But
I
look, Laurent polynomial is it?
yeah, I just misunderstood polynomial, so that's why.
Oh, okay, sorry, yeah.
So you map a function on the circle to like a function on the
Okay.
function of this. Sorry, I'm still confused on how that's done.
You like if you can write if you choose coordinates and everything, then you can write a function on from a circle as a function of like parameter theta. And that function, you just write the same function. Like it can be like that to the power of -1 plus 5 that to the power square. You just replace every time you have that, you replace it with t. All right. So anyway, I'm not going to use that. This is just like an explanation for why, like what is the, I guess, why did they like? What is the motivation to work with the Affine Grassmannian?
Can I ask a question?
Sorry?
Can I ask a question?
Yeah.
Yeah, so why do you need this K? Why it's not loop of G? I mean, in the theorem, it's loop of K.
Wait, I mean, like, why did they need in order to get like a homeomorphism to?
I mean, in the theorem, you're just.
This is not.
K.
This is like this is not a statement. This is kind of like this looks like that, looks like that. The actual statement, the correct statement is what I written before. When you need to take a maximal compact. This is just how to imagine the Affine Grassmannian as a loop space.
Yeah. So is there like a explanation why you need this maximal compact? Well, why you need this compact subgroup? No? Okay.
Things I'm not sure. I don't understand proof for
Thank you.
so therefore I don't know.
They put the intuitive jump from that to that G deformation retracts onto K.
Yeah, that's true. Homotopically, yes, but this is the statement here that is a homeomorphism, not just homotopy equivalence. Like it's true up to defining what do you mean homotopy equivalent to a formal scheme. Then this is a proof, but yeah, but it is really up to. Okay. So now next thing is properties of the Affine Grassmannian. So with the main point being having like a cell structure like we had with the usual flag variety, the usual flag variety. So so we have a map. So let this is going to be my notation for the co-weight lattice. So an object here. So right, this is from GMT. So if I have a map, so I have a map from here to loop of G. And the map is if I have an element here, mu, then I can define a map from B star to G and to E to G. Sorry, this is G. So this is mu. So any element of the co-weight lattice define an element of loop of G. This element does depend on a choice of formal coordinate, a formal coordinate of the formal disk. So we call the but now we can compose it with the quotient by positive loops. So a choice now, if you divide by positive loops, in particular, you divide by a choice of a formal coordinate. So the result, this is a terrible. Let's say, yeah, mu. Mu will go. The element here, I'm going to divide by t to the power of mu. So it's an element here that is basically like, I mean, in the case of like matrices, it's going to be, if I have, I don't know, in the case of GL2. And this is going to be like, I don't know, 2 minus 1, then this is going to be the matrix 2 squared to inverse. So all right, so the image of that, so now, I mean, first of all, let me say that this will map, first of all, to so this will map, this will, the fixed point of the Affine Grassmannian are exactly going to be the image of this. And that will, of course, map to the whole thing. I'm going to use this fact later. This is going to be important in the computation, that those are exactly the T fixed points. And the statement that gives us the can all loops can be written as a union over dominant co-weights of positive loops times the mu times positive loops. So like there's that Cartan decomposition. And in particular, we get that, so LG, if we take the double quotient by positive loops, this part is the Affine Grassmannian, and then we take L, like call it L plus G orbits in the Affine Grassmannian, and this is going to be the same as dominant co-weights. That is the web. So definition. This is the definition of a Schubert cell. So this is defined as the L plus G orbit of T mu. And G less or equal than mu. So this is like the open cell, and then the closed cell is going to be the closure of that. And there is, but I'm writing it as less or equal because we have the same result as we have the finite case, which is the closure is exactly the union of all open cells where with co-weight smaller or less or equal than the given co-weight. So. And position be less or equal. The mu G is smooth, proper of dimension 2 row. So row 2, like 2 row is sum of simple chords.
Proper less than.
Yes, the closed cell. Yes, of course. The open one is pseudo, not pseudo proper. Forgot the name for something which has proper closure.
Yes.
Smooth. Sorry?
Only the open is. Otherwise, like, I see a couple things which is.
Yeah, maybe there are two statements. Yes,
Open
orbit
is-
is smooth, but closed is.
Oh. Yeah, maybe. So let's say that this is smooth.
I think like GR SL2 is P1 like bundle over P1 plus point of infinity, and this point of infinity is GR0, which makes P1 smooth. Like it's a projective cone over some variety.
Oh. Is Um, oh, okay. So finally, to the definition of our ring where the ring that we're interested in. So equivariant cohomology of something. So what we want that doesn't really make sense, or we don't know how to make sense of it, is equivariant cohomology of the action of the loop G on the Affine Grassmannian times Affine Grassmannian, right? This is similar to G equivariant G mod B times G mod B. What is equivariant cohomology with respect to loop of G is undefined for now, but we want that. And this is by definition, this is like supposed to be cohomology of, so the Affine Grassmannian is loop mod positive loops, and then we take quotient by the diagonal action of loop of G. This is the equivariant structure, loop G mod positive loops. So, yeah, again, under loop. And now we can cancel them. So this is loop of G, positive loop of G, double quotient by the two left and right actions of positive loops, which is another way to write it is L plus equivariant cohomology of the Affine Grassmannian. This actually makes sense because the Affine Grassmannian can be written as a colimit over finite projective things. The action of positive loops on each one of them will factor through a finite quotient. So this is basically going to be by definition colimit, let's say, over that's why. So each one of them is finite. Here, this is a finite quotient, and then you take colimit over all of them. So this is well defined. So this is going to be the ring we're going to be interested in. That for now, we just and then we are going to almost this ring, I guess. Like,
Grassmannian was a colimit, but the homology by default flips.
oh yeah, this is supposed to be my.
Why are we interested in that and not cohomology of flag times flag? Like Affine flag.
I mean,
Or is it the same information?
they're not. It's not the same information. The heuristic reason is the Affine Grassmannian is the generalization of loop. That's all I mean. You can compute both.
It's just based on like your first blackboard where you said, let's remember G mod B times G mod B.
Well, the reason for I mean, this looks like a nice place to think about. I mean, the other like the computation for the one for the flag variety is not that far. Like in the notes that Daniel sent a few weeks ago, it's actually the way the computation is done is by first computing the one for flag variety, which is supposed to be easier, and then doing that. But definitely they're not far from each other.
The algebra itself look a lot nicer and nicer generators and relations and for a fine flag variety. So it kind of makes sense to first compute them.
Yeah. Well, in description, I will give. I don't like the difference between them is going to be take a quotient by W or not. So it's not going to be a big.
Peter, you're not doing loop rotation. You're not doing
Loop rotation will come in a second. Yeah, I'm just first of all I'm doing that, and then I'm going to say this is actually going to be commutative, and then we're going to have loop rotation so that it won't be commutative anymore. So
yeah, also maybe examples of these things, if you take mu equal to 0, like g0 is point and GL2 of 1 is P1 or PGL2. I think PGL2 and both GL2. So if you act by group and both, you can do it by hands. Like it can be useful to do at least one computation with two by two matrices and run polynomials at least once in your life.
Good advice. Anyway, so first of all, this is going to be a module. This from now on, this is what we are interested in. Module over just as before that. So equivariant cohomology of a point. So what is that? There is a trick. We have an evaluation map. Evaluation at 0. The kernel is unipotent, or it's like a co-limit of unipotent. So let's call it like unipotent. And therefore intractable. Just like we had in the case of like the Borel, where we could reduce to the torus. So this positive loops equivariant of a point is the same as just G equivariant homology of a point, which we already know what it is. So this is like functions on the torus mod action of the wild. So like you take the equivariant homology of the torus, and then you divide by, and then you take fixed points by the actions data. So yeah, so this is a model over that. Now I'm going to say next thing is to understand the convolution structure on that, which I'm not going to do first. First thing I'm going to state that it is commutative, and this is based on a theorem that we are absolutely not proving, which is geometric staticity. So let me just write it down, because I believe the paper is using that, and I could not see any way to like not use it. So I guess we'll have to state it. Theorem. There is a monoidal equivalence between so reverse sheaves that are L plus G equivariant on the Affine Grassmannian with representations of the Langlands dual group. So the group corresponding to the dual root data. The only thing that we need from that, is here the monoidal structure is convolution, basically the same convolution that we had, same convolution that we defined here, like in the finite case. Everything will work the same, though in the Affine Grassmannian there is also like a description of the convolution in terms of boundaries and trivialization. But doesn't matter for now. The main point is that here it's convolution, here it's just tensor of representation. Tensor of representations is commutative. So what we're going to get here is going to be commutative too. So I'm going to write. Maybe a remark. So on red, G is commutative. So this is commutative. So here you just, I mean, this is just like this is cohomology of like the structure shape here. You can also just take it as a black box that this ring is commutative. It's going to be just a minor detail in the proof, but still there. What did I want to say? Our remark is that, of course,
you are using it as functors, so you're not using it for objects, you're using
like you have five, like
you're using morphisms, not objects.
yes.
Okay.
I mean, so and yeah, I mean, this is like an H0, H0. I mean,
Yeah.
there is a higher like E3 structure. Doesn't matter for now. Not going to be used. Anyway, so this is going to be commutative, but the point is we're going to define. So now we're going to define a deformation of that is not going to be commutative. So.
How do we get from like a conclusion like the Hiroshi tensor being to like that being commutative?
So if you can define cohomology of that as like home from like the structure sheet here. The cohomology is like one of the home spaces here is maybe either better. Is there a way to do just with objects? I don't know. Yeah, I mean, well, I mean, a map from, let's say, I mean, I'm not sure this is straight away, but you can define cohomology if you have a category of cohomology is defined as map from the structure sheet. And the monoidal structure on that comes from the commutative algebra structure on the structure sheet.
So cohomology is forms from structure sheet to itself.
Yeah, like homology of the entire space is like yeah. So now we define a deformation of that. And this is going to be,
But
yeah.
Since Barry is like an thing, like I mean like structure sheet. And maybe you meant like constant sheet, like
Yes.
yeah, but you want to do that like at each level and then kind of do the anything as you like, not like constant sheet on the whole.
Yeah, I mean, the definition of constant sheet is going to be like push start pullback from a point. And this, if you define your start pullback for each thing as taking colimit over everything, then it will be automatically. And if not, then you will have to. So we are going to, the object that we are going to be interested in is H. So we have, let's write it down. So C star acts on loop of G by, so this is like loop rotation. So that means this is like a loop, like a map from the puncture disk. You can pre-compose with an action of GM on the puncture disk. So C star will act on LG by that. And therefore will act also on the Affine Grassmannian, and we'll get this cohomology of loop plus G semi-direct product with C star of the Affine Grassmannian deformation. So this is going to be a deformation of the commutative thing, which was L plus G down. So now this is a model over a slightly bigger algebra.
Is triangle in the what is
Sorry?
who is normal where? No, it's all right. Yeah, is L plus G normal or is C star normal? I'm confused.
I think C star is
So equation by C star.
C star is normal.
So triangle should look at.
Is the triangle opposite? I think I wrote it opposite to that, and then I discovered it's opposite, and I flipped it, but maybe I flipped it twice. Triangle in some mysterious direction. Anyway,
I think that's right.
yeah, thank you.
Model
Over G is now a point. So same computation as before. The like the positive powers of T do not contribute anything. So this is going to be O of T mod W times A1. A1 is like spec. So like the like corresponding like the algebra of that. So we write it A1 with coordinate H bar. You remember the formation part. We're doing physics. All right. Okay, so now claim this is what is claim, which is something that is called equivariant formality, I think. That it says that this is a free module over model L plus G to run point tensor with homology of the affine Grassmannian. So the statement is that it's a free model, and the proof of that is, from all I know, a spectral sequence argument. Like we have a spectral sequence computing equivariant cohomology. This is the E2 page, and it was there to generate the E2 page. So, but I'm going to leave it.
How can we at some point like repeat Haskell where often just say, oh, E2 page degenerates and then 0 comments. And like, why does E2 page, how do we prove this?
I saw a reference for that, which I did not open, but I can I can look it up later and tell you.
Computing complexes and like writing differentials definitions.
Supposed to be, I mean, from what I remember, because I read the description, I don't remember exactly, something about like you only have even cohomology. I don't remember. I don't want to say things I'm not sure about.
Oh, yeah.
So supposed to be related to that, but that's all I remember. Anyway, like I believe, like, you know, it's kind of like here you only have even cohomology, like a complex name, so all of the errors.
Yeah, I think there was a claim in Webster's notes that like each space with only even cohomology.
Yeah, because you have it's like a CBDW complex, and you only use even dimensional cells. So
yeah, well, I mean, don't confuse the current cohomology like that, but
this is not. Oh, sure. Yeah, I don't know. All right. So now I said that this is a model over that. In fact, it had yeah, the cohomology of Affine Grassmannian is modeled over yeah, let's try it out. This as G and the product with C of the Affine Grassmannian is a definition basically like the double quotient, the C star homology of the double quotient. So we have two different maps. Like I can contract that to a point, and I can contract that to a point. So I get two different maps to a point mod L plus G. So G. This is projection 1 to point mod plus G, mod plus G, and then that third projection is not even in the diagram, so I want to do a huge diagram for no reason. But anyway, we get two different maps from equivariant homology of a point to L plus G times the equivariant homology of the Grassmannian. So this is pulled back by this first projection, pulled back by the second projection, and then we also have just a map from equivariant homology of this stuff. Just by contracting everything to a point. And this is projection full size. Now this is the point where they're using. Sorry?
You can see star everywhere, but what happened? Like H star L plus G. Why did C star go?
Here,
Yeah.
you can just forget it.
No, the map is in the other direction. You can quote
Like the C star acts on LG. If you contract LG, you can contract the C. Like you can write that as mod C, but then you contract it. You can do this like C, and then contract it. If I was just doing that, I could not. But if I'm taking a quotient by the it acts on, then I can take quotient by that too. So the only point where we are using geometric stack is by the statement that the images of these two maps are going to commute with each other when we restrict to when we restrict to like to a trivial action of C star. But first of all, I'm going to write down the statement, I guess. So we get a map from O of T mod W times T mod W times A1 to equivariant cohomology L plus G star and Affine Grassmannian. So each one of these contribute a T mod W, and then this one will contribute the A1 part. Yeah. Now, claim the first projection restricted to H equals 0 is the same as the second projection, H equals 0. And here, proof. Because what restricting to H equals 0 is basically restricting to the just L plus G equivariant cohomology of the Affine Grassmannian. So follows from commutativity of G. But the main, and so you can just assume, yeah, this is commutative. So the two images are gonna agree with each other, and because they agree, basically, when like here we have functions on this product, but we restrict to 0 here, we can restrict to the diagonal here, because they will both contribute the same. Like the value is going to be the same. So the fact that the two projections agree means that the functions in the here are going to restrict to the going to have this restrict to the diagonal when you restrict to 0 here. So
Is it a map of? Did you look at this?
this is not a ring. Like this is not. Yes, like so. It's just that the like when you can flip, like flipping them is like flipping the convolution, the direction where you do convolution, and if you already know that you have a convolution, like this is using the ring structure without having a ring structure on the whole thing.
So, like you just send 3 elements to their product.
Yeah, you just you flip them, and we know that the flipping is not going to do anything.
Yeah.
This is what we are doing. So, yeah. But for here, this one, like we don't we do like the convolution is not coming from here. The convolution is going more complicated to the. So we want to restrict to a space here where outside of 0 we still have the same product, but at 0 we are going to have just the diagonal. This is the deformation to the normal cone. So maybe I will write a general definition. If we have a closed subvariety, there is space which is denoted either by that or by switching the z and the x. I saw multiple references using different notations, mapping to x times a1, or should I write it as a definition or a claim? I don't know. So the special fiber is going to be the normal cone. So it's going to be the inclusion of the C of x mod Z maps to x, and generic fiber is going to be x. So what this is doing is we have a space parameterized by A1, and we have everywhere we have the original space, but at the over 0 we also add infinitesimal direction in the direction of z. So it's like one step before we are doing a blow up. So in a blow up, you take a subvariety and you add a choice of direction there, but we divide by the action of C star to get a projective space, and here we stop before, and we just have the directions like the normal to the subvariety Z. X. So in our case, the subvariety is just going to be the diagonal, and so corollary. So we know that when you just go to 0, the two projections will agree. So we can actually restrict it to diagonal. And so let's call this map alpha or alpha tilde. So alpha tilde factors through the normal, the diagonal in T mod W and T mod W. And then theorem. Alpha is an isomorphism. So the theorem is more than just this is an isomorphism of vector spaces, because as we remember, this is just going to be like some vector space. But the structure of the normal cone is giving us also the structure of that as a model over various spaces. So, for example, here, if I can project to the diagonal, I get the structure of that as a model over just equivariant cohomology of positive loops of a point. If I restrict to the generic fiber here, I'm going to get the two structures, like the two projection maps. Okay. Now let's see. Do I have a time to write a sketch of the proof? So let's see how much of the proof I can write. And then there is another theorem that I don't know that I will probably not have time to write, which describes also the rings, like the convolution structure. Let's do. So this is gonna, so let me just describe in words, I mean, the steps. So first of all, for alpha injective, so we use something called equivariant no, this is equivariant localization. No, I don't remember names of theorems.
Yeah, I think so. If you are connecting homology of the whole space to the homology of points.
Yeah, okay, so this is equivariant cohomology. So everything here is going to be a module. So let's say H C is a module over the point, and as we said, this is and therefore of just here given homology of a point. And the statement is that after inverting this ring, so everything is a module over that, which I'll remind you, this is just O of the T times A1. It's a module over that, and the statement is that we're taking a equivariant, so yeah, maybe let's say that. So this is a module over that. And the statement is that as long as you have some finiteness conditions hold, if you invert the base ring, you can restrict here to fixed points of that. So in equivariant cohomology, we're computing cohomology of the quotient, but after inverting all elements of the base, which is equivariant cohomology of a point, you can restrict in the space in also to fixed points. It's like a fixed points and orbits kind of statement. Tensor over that with its fraction field. Going to be the same as doing the same thing, but just for T times C star fixed point of the Affine Grassmannian. Now, if you remember that only T fixed point of the Affine Grassmannian are the point t to the power lambda, like the diagonal matrices with t to the power something. So this is going to be, I guess, first of all, it will inject into limit of the homology of just the Schubert cells. Things are over that diffraction field. And then in each one of them, I can take t times c star fixed points here, and I will have the same result. This will give me a single point. So I'm basically getting limit of e to the power gamma tensor over that with its fraction field.
And I guess here is the direct sign.
And then this is just product, direct product. So nothing is happening. So this is basically going to be product over each. They are not connected to each other. So I'm basically, and this is fraction. So I just have a bunch of copies of the fraction fields of that. And so the only thing that is left to see is the action of that on that. Like, not the action of that on that. Like, so I have a map alpha from O of W square. So we need to know, so and here each one of them is a subspace of this normal cone, of this deformation to the normal cone. So the point is just to see what happened, like how the restriction works. How do you restrict an element from here to just t to the power 1 to this point? So all that is left to see is what happened, like if I have to, I'm just going to do log. The log means tensor over that with the fraction here. And this is alpha. So all that is left to see is the alpha localization, what it is, how you restrict to each one of those points. And the statement, which is not hard to see, is that alpha log is like each component is the restriction to what they denote as gamma, which is x, y, a, and x equals y plus a lambda. So it's basically like if I am taking lambda, if this is like equals 0, which is the case here, this is just like we have like this is just the diagonal. And then the statement is that those things are like, you just move the diagonal. So here we have a deformation of the diagonal. And this map is just scanning over all shift of the diagonal. So it's injected. The bottom line is A log is a bunch of restrictions. And then to prove surjectivity, I definitely not going to have time. So surjectivity is done by counting dimensions. All right.
Any questions?
Could you move the camera to the other board, please?
Oh, sorry, did I forget?
Oh, no.
No, I just want to look at the other board.
No, the
Oh,
banner
okay.
was at you. Yeah, now it's. Yeah, I can show you anything. This one.
Yeah, you wrote at some point an alpha twiddle map.
Here.
Yeah, I'm following you.
Oh, no, I
No,
did another miracle.
it's fine.
Yeah, this is here. Alpha twiddle. This is like, yeah, we have maps from here. Yeah.
And which one was the isomorphism? It was
No,
this one.
we have a map from this is a product, and then we just say we restrict it to instead of taking the entire product over 0, we take the normal cone to the diagonal.
Yes.
And the statement is that after doing that, you get an isomorphism.
But yeah, so
The reason it's
how do you
possible
see
for
the
that-
C star equivariance on the left-hand side?
Sorry?
So the left-hand side doesn't see the C star equivariance, right? On this alpha map. Like how can it be an isomorphism?
It's not a no real structure. It's vector space and something else.
Yeah, I mean, it's like to get like the convolution structure. I don't know if this is what we are asking. To get a convolution structure, you need a lot more.
Right, but it seems like you specialized like the C star parameter. Like on the left, there is no factor of A1 remaining.
Oh no, there is. Oh, sorry, I see. The
Yes.
relation to the normal cone does have an A1.
Oh, it does.
You,
Sorry.
you don't take the coefficient like in a blow up. You still have the entire it's not like a direction, but actually a vector, more or less, right?
Ah, okay.
It's inside, like this is mapping, not sit inside, but mapping to that.
Okay, sorry. Thank you. Okay, that yeah.
And that's kind of the whole point, is that like it's a way to write it as a deformation, which is what we want. We want the
Mhm.
fiber, which is like a commutative thing, to deform into
I see. And when you specialize like the C star parameter to 1, do you just get like cotangent bundle T mod W?
you just get the like the tangent normal cone to the diagonal.
Okay. All right, thank you.
All right.
Any other questions? Okay, let's thank the speaker again. Yeah,
Thank you.
Yeah.
Thanks, everyone.
Thank you.
Yeah, thank you for coming.